Our next speaker is Doug Lewis. Doug is a forest ecologist working for the BC government, focused on assessment and monitoring of forest resources in response to cumulative effects of natural disturbances and resource management and land use. So with a nice short introduction, I'll turn it over to Doug.
Just a second there. Thank you, Jason, and thanks to Jeff Morgan for the invite to this presentation. It was good to hear that the previous talks really talked about the need to collaborate with First Nations and planning. And so what I'm going to kind of talk to you today is a little bit more about one of the tools in the playbook that we can use to inform those planning processes. And this is what I'm going to talk about is a GIS indicator-based approach for rapid post-wildfire watershed assessment, with an example with the Elephant Hill wildfire. So as Jason explained, I am a forest ecologist. I'm currently a stewardship evaluation forester. I focus a lot on assessment and monitoring, and largely wildlife habitat biodiversity, but I spent a lot of time working on watershed assessment, watershed hydrology for the last 10 or so years. So as we get into this, just recognizing that I am not a hydrologist, but I have had the opportunity to work with some really great people. And so the approach I'm going to talk about was built largely by Michael Milne, hydrologist, Bill Granger, geoscientist. And the names that you see on the screen, I just want to acknowledge these are a lot of people that I had the pleasure to work with or were influenced by their work over the years. And so, big shout out to the hydrology community in BC. David Huggard, forest ecologist. This can't be done without really good GIS people in the regions, folks within the cumulative effects program, and some early work that was done with foresight consultants and some of the folks there that really helped us develop this early on. Jeff asked me to talk a little bit about this particular approach, which I'll get into more detail here. This GIS indicator-based approach it's not really new. It is based on the watershed assessment procedure that goes back to 1999. Some really great early work by Martin Carver, Greg Utzik in the Kootenay region. Around the hydrologic screening decision support tool, Kim Green, and her work in the Kootenays Kamloops TSA watershed screening tool. The approach that kind of has been built off of these, what I'm going to talk about today, is currently in use throughout the Thompson, Okanagan, and Caribou regions through the Cumulative X program there with government. There's some contact people there. It's also being built out in the Kootenay boundary region. Natasha Newman, John Rex has been leading some work on this and adapting this in the Omanika region, and provincially, Lisa Nordine working on very, very similar for the whole province there as well. And so this kind of information, so tens of millions of hectares throughout, particularly the interior of the region, this type of tool is available. So just to let people know, I don't know if a lot of people know that it really exists. Give me a quick overview of this approach. There's a link to the Cumulative Effect website where you can find it. It is a strategic watershed assessment, really focused on quantifying relative potential hydrologic hazard. It's suitable for large areas, numerous watersheds. The approach there is to identify where there may be elevated risk or hazard to downstream elements. So we can look at domestic water intakes, private property, public infrastructure, and of course fish and fish habitat. And the goal really was to assist in prioritizing and proactively directing resources into those higher risk catchments so that we can complete further assessments and manage risk on the ground. And so, as I've alluded to here, it is a risk-based approach. And so we calculate for each assessment unit, I'll talk about assessment units in a minute, we calculate a number of GIS indicators of key hydrologic processes related to streamflow, sediment, and riparian. So each of these is rolled up into hazard ratings related to streamflow. So the likelihood that we're going to see more frequent and severe streamflow events, sediment hazards related to the increased likelihood of harmful sediment being introduced, and the likelihood of loss of riparian function. And those hazard ratings can be also you can also join that with information on consequences related to different elements at risk to put that in sort of a risk rating framework, and really pull out those areas that are most at risk in your area. Oops. Okay, so just to give you a quick example of some of the way that this assessment procedure is structured, on the left here, a number of GIS indicators, some of them related to the natural characteristics of the watersheds that we're looking at, and others related to land use factors. And these are sort of rolled up into ratings. And I'll talk a little bit further about this, but ultimately trying to get at a streamflow hazard rating for each particular assessment unit. What I really like about this particular approach is this idea of overlapping multi-scale assessment units. So the GIS indicators and ratings are generated for each assessment unit. And as you can see here, as we move across, we start at the very large watersheds like the Bonaparte River, like the Deadman River. And then we can kind of move to watersheds within, and here we're showing examples of things like Chris Creek that fall within the Deadman River, basins within Chris Creek, subbasins, and even some of the residual or face units that fall within those areas. And so it reports at each of those different scales, the indicators and ratings, and those can be, it's important because depending on what your point of interest is and the specific elements at risk that you're worried about, you want to look at what's happening upstream of that point of interest. So if you want to know what's happening at, the outlet of the Bonaparte River, and what's happening upstream and being influenced like that, you can look at that. If you're looking at if steelhead habitat at Chris Creek, you can focus on that information specifically there, or one of the basins within that. So this sort of multi-scale assessment approach is really valuable. Okay, so I'll go into a little bit of example of the Elephant Hill wildfire here in 2017. You guys have heard a little bit about this already. 192,000 hectares, really roughly about, on average, about 20 kilometers wide, 90 kilometers in length. In these, you can see here it's overlaid with the Deadman and Bonaparte River watersheds, but there were up to over 140 individual assessment units that were affected within those larger watersheds. And you can see too by this map of the burn severity map here as well, that burn severity really varied throughout the fire area. Okay. And so when we think about that in terms of post-wildfire decision needs, we're looking at really, hundreds of thousands of hectares of watershed. What we were looking for is a rapid assessment of impacts of the wildfire, as well as pre-disturbance landscape condition. And so the map on the right here, you're seeing the wildfire imposed on top of all of those gray areas are areas that have been harvested. So a lot of the upland areas in these watersheds had been previously subject to mountain pine beetle disturbance and salvage harvesting. So there was a lot of, as Eric spoke to earlier, a lot of disturbance that was already happened in these watersheds. Lots of activity on the floodplains and along the riparian corridor there from different types of land use. And so what we really want to look at, we need to look at all these multiple watershed assessments and the elements at risk that exist within them, and identify areas for immediate attention. And so, where do we have private property or human safety that's at risk? We did some work for Ministry of Transportation and Infrastructure looking at highway sections or bridges culverts that could potentially be affected, informing the wildfire salvage response. And then, of course, we could also look at hopefully identify some areas for long-term management for recovery and rehabilitation efforts for fish and aquatic habitat. Oops. There we go. Okay, so I'm going to talk about one of the important parts of this this particular assessment procedure, which is around characterizing sort of runoff response, and this is around how sort of flashy or responsive different watersheds or assessment units within these areas might be to runoff. And so we have this runoff attenuation rating, which is based on the amount, or in some cases, the absence of lakes and wetlands, as well as drainage density ruggedness, which really looks at the drainage density of the watershed, as well as the sort of the elevation gradient. So again, just sort of how well plumbed and responsive these watersheds are to runoff. Here you can kind of see on the left, the drainage density ruggedness scores, and so they become the higher values are areas that are just generally tend to be steeper and more well drained. You know, predominantly in the southern part of the Bonaparte river watershed, and whereas the upland areas tend to be flatter. When we look at the middle there in terms of location weighted percent lakes and wetlands, those flatter areas in the uplands also tend to have a lot more lakes, wetlands that can attenuate flows. And so on the right, when we get to sort of a runoff attenuation rating, you know, the upper parts of the watershed tend to be have better runoff attenuation. So basically slowing down that runoff, less flashy as compared to the lower part of the watershed, where the runoff attenuation is low, but it's more highly responsive to runoff. Some of these indicators were really kind of useful. While this particular assessment procedure, when we're looking at streamflow hazard, we're really predominantly focused on snowmelt-driven peak flows. The drainage density ruggedness score really identified some areas that were sensitive and responsive to, as Tim pointed out earlier, those sort of summer rapid rainfall storm events, and where we experienced some debris flow events and mudslides. Those areas in red in the left there. And so those are also, so some of these indicators just on their own without getting to a rating can be kind of helpful in identifying areas that might be responsive to those types of events. Okay, talk a little bit about runoff generation as well. And so the part of this is really looking at areas that are likely to generate more runoff as a result of loss of forest cover. And so this kind of goes back to what Eunice was talking about earlier. Precipitation is a big driver. Well, of course it is, because that's what where we get stream flows from. But in these areas, these are sort of snowmelt dominated hydrologic regime. What we see in this part of the world is that the precipitation really varies by elevation. And so the lower, drier valley bottoms around Kamloops, Cache Creek, and those areas where you're in sort of the bunch grass and dry forest don't receive a lot of precipitation. Most of that annual precipitation is going to fall at the upper elevations. Most of it falls as snow, and that snowpack can persist well into the year, and that's what really drives the spring freshet and peak flows. So some of the work that was done, I worked with Rita Winkler a little bit on this, and her work was using the biogeoclimatic zones and those units as an indicator of the area that contributes to snowmelt runoff to spring peak flows. And so the map on the left shows the biogeoclimatic zones that largely contribute to snowmelt runoff. And we used some climate information there because the area of the watershed that contributes to spring flows is largely generally the area that's still has snow after April 1st, we looked at those biogeoclimatic zones that basically had their average daily temperature was once it got above sort of -1, those areas were sort of beginning to contribute runoff, and those areas that we kind of delineated those that occurred in April versus some of the lower elevation. So an important part, because these are the areas that when we're concerned about snowmelt driven runoff and loss of forest cover, these are the areas that we really are kind of more concerned about. For example, Rita did some really great work in this report, and she looked at the hydrometric stations, and the upper hydrometric station there, Bonaparte near Bridge Lake, which is really in the very upper part of the Bonaparte watershed, up to 50 to 80% of the spring and summer flow was generated above this point, which really is telling about the importance of the snow contributing zone, compared to much of the rest of the watershed. So these snow contributing areas, again, there's some other areas down in the middle around Upper Cache Creek, Scotty Creek, Loon Creek, those kind of areas as well that were really important. But it really gives you a sense of those are the areas that really contribute the most runoff. As we learned earlier too, that those are also some of the areas that are better attenuated, but it does really vary depending on where you are in the watershed. So from a runoff generation potential rating, we're able to look at some of the watersheds and watershed units that are more likely to generate additional runoff that contributes to spring peak flows due to loss of forest cover, and those are the ones here in the darker colors that you see on the map. So, and finally, to get at streamflow hazard rating, well, so we've looked at areas that are more likely to generate runoff, and those areas where that runoff is going to be transferred downstream more quickly, so you get more a flashy peak flow or flood response. We also want to look at what's the effective land use, and we use an indicator equivalent clear cut area to evaluate that. So equivalent clear cut area, it's pretty commonly used. It measures the extent of area that's disturbed, and it does account for to some degree for regrowth over time, and it's based on snowmelt and snow accumulation processes in forests. In this procedure, ECA accounts for we use it to account for a lot of relatively permanent land use, urban agriculture, and other types of areas that where the forest has been converted and sort of relatively permanently cleared, as well as cut blocks and that regenerate over time, and mountain pine beetle affected forests that also will recover over time. What we did there as well is we overlaid the burn severity mapping and applied a burn severity coefficient to modify the ECA for wildfire affected stands. So because this information wouldn't be in our inventory right away, we were able to modify the ECA for a number of stands to look at the effects of the fire itself. Here's a good example, and this really kind of reflects to some degree where the risk or the hazard, streamflow hazard, really exists in the watershed. Pre-wildfire equivalent clear-cut area resulting from mountain pine beetle and salvage and other things on the left. And then when we overlaid the burn severity mapping associated with the fire, we see a post-wildfire equivalent clear-cut area of, in a lot of cases, over 50% of the watershed area. And you can see towards the middle of the figure there, the areas of Scotty Creek, Barricade Creek, Loon Creek, and Cache Creek. Those areas also, prior to the wildfire, the snow contributing zone of some of those areas was already at 40 to 50% ECA, and post-wildfire in upwards of 70 and 80% equivalent clear-cut area. So not a lot of forest cover left, which means some of those areas were going to be really responsive to wildfire and wildfire effects, because these are also some of the areas that tend to be have less runoff attenuation as well. Oops, we'll go back here a little bit. So once we have some of that information, we're able to characterize some of the watersheds, how the flow might change as a result of wildfire and other effects. We can then overlay some of the elements at risk. These figures are from a report that Rita and myself worked on for the Elephant Hill wildfire, showing some of the private property and other, on the left, private property and other downstream elements that were at risk in the area. On the right, we looked at fish and fish habitat, core steelhead spawning areas, and other important fish habitats that could be affected, and gives us an information depending on what our main management concerns are, where we could actually direct some of our resources on the ground. One of the, as Eric spoke to and others spoke to earlier, informing things like salvage and retention guidance. So this watershed information did inform that strategy. As Eric pointed out, it was really focused a lot on watersheds. The area, and you can kind of see in a sort of a browny orange color there, were those snow contributing bioclimatic zones, where the guidance was essentially full retention and no harvest in those areas, unless a more detailed hydrologic assessment was being completed that could form a salvage, retention and runoff management plan. And in some cases, there are situations, and I think Tim pointed those out early, where salvage and quick regeneration could hasten the forest recovery on these sites and get it back. So I think what was important about this was really to inform sort of early direction, get that information out quickly to inform some of the salvage guidance, and point people where to do further investigation as some of the key parts. And I won't get into too many of the other pieces about that, but I will kind of conclude here a little bit on just some thoughts about these types of strategic GIS indicator-based assessment procedures. They are, in my mind, they are very useful to characterize, some of the watershed hydrologic processes, understand the implications of wildfire coupled with existing disturbance, and where it's most likely to have the greatest effect when you're dealing with really large areas and you want to focus your existing resources into the most important areas in the short term and in the longer term. Highlight watersheds based on the extent of disturbance, the predicted hydrologic response, and the downstream consequence, which are all part of that risk equation. Again, directing resources for further field-based assessments, as well as focusing where to focus managed attention to avoid or mitigate risks. And while this is kind of valuable at a strategic scale, it is important to point out that these types of assessments, they don't replace field-based assessments. Having more detailed field-based assessments by qualified professionals is really what is necessary to really understand what's happening at a more tactical or site level, to provide options to mitigate risk, and hopefully this type of approach can get you a little bit closer to where you want to focus that attention. And so I think I am going to end it probably a little bit earlier. I'll stop right here, and we can move on from there.